Hello everyone, I hope you're doing well. In this video, we'll be finding out the indices for the directions in the cubic unit cell. In previous video, we calculated the Miller indices for direction A, and in this video, I'll be calculating the Miller indices for direction B. The method is super easy and you'll be amazed by how easy the method is. Okay, so let's quickly get started, and before we dive into the problem, we should first know the steps that we are going to follow in finding out the indices for the directions. Okay, these steps are really crucial and we'll be following these steps. Okay, these are the basic steps, so let's have a look on these steps. We'll just read them and we'll understand them as we'll apply in the problem, so you'll better know them. So here are the steps that are involved in here. And the first step is to define the coordinate system. Whenever you are finding out the Miller indices of directions or planes, the most important step is to define the coordinate system. And as you can see in our case, the coordinate system has already been defined. It's predefined coordinate system. In some cases, the problem that is given to you, they have already defined the coordinate system for you, so you don't have to. But in some other cases, the coordinate system is not defined, so you have to do it yourself. All right, so it's totally fine. This origin, this one, okay, this point as origin works really fine in every case, so you can take it as origin. And this is the positive x-axis, this is the positive y-axis. As you can see on the screen that they have used a similar coordinate system, hence we'll be using this coordinate system as well in our problem while finding out the indices for direction A, B, C or D or whatever it is. I'll always use this coordinate system because it's my favorite. So the first step is to define the coordinate system. The next most important step is to find out the tail coordinates of the direction and then the head coordinates of the direction. These are the central steps, and they'll define your final Miller indices. Okay, this is the crucial part, and rest of everything is really easy. So we'll be finding out the tail coordinates and head coordinates of the direction. As we know that a direction has this shape, this graphical representation, and it has two main components. One is its tail. This initial point is called as its tail, and the other point is its head, which is right here. Okay, this is its head, and we'll be finding out the coordinates with respect to origin. Coordinates means that what is its position with respect to origin. It's simply a map that you have to follow in order to reach to point whose coordinates you are at. For example, tail coordinates mean that starting from origin, what motions along x, y and z directions you have to make in order to reach point T, which is tail. Okay, it's just like a map of a certain location, where the locations here are the head and the tail of the direction whose Miller indices you want to find out. Okay, and after finding out the tail and head coordinates, you'll subtract the tail coordinates from head coordinates. All right, and after doing that, we'll make some checks, like if there are fractions, then you have to remove the fractions, and you have to make sure that the indices or the numbers that you have got so far or in least integer form. All right, so all of these things we'll be doing right there in direction B. So let's quickly get started as we have seen the major steps. Here is the direction B, we can see here. Okay, this is the direction B whose Miller indices we'll be finding out, and we can see luckily that this is our origin and the tail of this direction is at origin as well. So the tail coordinates are really simple here, and we do not have to move anywhere from origin since the tail is at origin. So its coordinates will be 0 in x direction, 0 in y direction and 0 in z direction. All right, so no motion along x, y or z direction will be needed to reach tail because it's at origin. Okay, it's at origin. Now let's find out the head coordinates, which is where the head of this direction is. We can see here that it's here, and if you really see it, then it's on this plane. Okay, this is the side wall. We have this side wall, and the head of this vector is at this side wall. You can clearly see it. All right, this is the side wall, and here right at the center of this wall the head of the vector is. Okay, and they have also told you these points. These are the points for the x and z directions. Why? How we can say that 1 by 2, 1 by 2, the points they have mentioned here are for x and z direction? It is because we know that this plane is at y equal to 1 point. This is the plane which is located at y equals 1 position. We can see here that since y is 1, then half and half, the numbers they have shown here are for the other coordinates, which are x and z directions. Okay, and we could have even guessed it even if they have not mentioned it here. All right, whenever let me tell you a rule that you have to follow while assigning these numbers to the coordinates. This rule is really simple. Whenever you are moving from one corner of the unit cell to the other corner of the unit cell along the axis direction, this length is taken as 1. Okay, if you have moved, for example, if you have traveled the distance half of it, even, okay, if you travel half of this distance, this whole distance is 1, and if you travel half of it, then you will take half as the coordinate. All right, so what if they haven't mentioned these points here? So what would have we would have done? Okay, so let's do that. Now let's have a look on how we can determine the coordinates without these hints that are already given, because they are not always given, so we should know the method to find them. So this is how you are gonna do this. Starting from origin, we start motion starting from origin, and we wanna reach this point, head point. All right, and we know that it is at the center of this side plane. What we have to do to reach that point: starting from origin, we'll move 1 unit along y direction to the other corner of the unit cell. Since we are moving along the y direction and from one corner to the other corner, that is why that length would be taken as 1. Okay, we moved 1 unit along y direction, and then you can see that here is the point. So I'll move halfway along x direction. This is parallel to x direction. Okay, so we moved half of this distance. This is the total distance. This was the total distance, and I traveled half of it, and I moved half distance along x direction, and then from this point onwards I moved half way upward in z direction. And we can see here, if I would have drawn the complete line, it would have been 1, and since I moved the half of it, so that is why this is half motion for the z direction. All right, so we can clearly see the coordinates for the head, and that was really simple, and it is half along x direction, then half then 1 along y direction, and then half along z direction. All right, so it was really simple. Now we need to do the other steps, which are head minus tail coordinates. In exam, this is how you are gonna attempt this question. First of all, you write for direction B, whatever name you have given to this direction. You can even let it, for example, if the name is not given, you can let the direction be B or A, whatever name that you wanna give it, and then you'll write the tail coordinates are you'll write the tail coordinates, which were 0, 0 and 0. After doing that, you'll write the head coordinates. You'll write the head coordinates of direction, or simply of B, are head 1 by 2, 1 and 1 by 2. Alright, so this is how you are gonna write it. After that, what you will do is head minus tail coordinates. So let me rub it. You'll write operation, that is head minus tail coordinates. Alright, and you'll make 3 sections. One is for x direction, the other is for the y direction, and the last one is for the z direction. As we know, the tail coordinates are this and head coordinates are this. So keeping in view the order of subtraction, like we will write the head coordinate and we'll subtract it from the corresponding tail coordinate. So x from x, y from y, and z from z. Alright, so for x direction, first we'll write head coordinate, which is 1 by 2. It's 1 by 2 minus tail coordinate, which is 0, and you'll write equals to 1 by 2 simply. And then we have 1 for head for y and 0 for tail, so 1 minus 0, which is equals to 1. Then you'll write 1 by 2 from head of head minus tail coordinate of z coordinate of tail, z coordinate of tail, which is 0, and 1 by 2 minus 0 is 1 by 2 again. So the numbers we have got so far are this: 1 by 2 for x, 1 for y, and 1 by 2 for z. As we can see here, there are fractions involved, so we have to remove the fractions, and we'll write operation remove fraction. And for removing the fraction, what we do is to multiply the LCM of denominators with each of these numbers. Okay, so we can see here that denominators here are 2 and 2, and LCM of 2 is simply 2. Alright, so we'll write it here. What we are gonna do, multiplying the LCM of denominators, multiplying by 2, simply you can write it. Okay, but you should know that how you know that you are supposed to multiply it by 2. It is because the LCM of denominators was 2. So we'll multiply each of these numbers by 2. You will have to do it here. Okay, let me do it here as well. 1 by 2 multiplied by 2 for x, 1 multiplied by 2 for y, 1 by 2 multiplied by 2 for z. 2 and 2 cancels out, and it's 1 which is left behind. It's 1 multiplied 2, which is 2, and 2 to cancel, it's 1 left. So we are left with 1, 2 and 1, and we can see here that they are in least integer form. For example, there is no number that could be divided by each of these numbers that can make it lesser. Okay, because if we divide any other number, any other integer, any other positive integer, then it will become fraction. Alright, so for example, what that means is sometimes we get some numbers like that, maybe 4, 2, 2. Okay, if we divide each of these numbers by 2, by similar number 2, then it could be reduced to a least integer form, which cannot be reduced further because there is no other number that could be divided to this number to make it least integer. Integer is a number, is a whole number. An integer can't be a fraction. Okay, so by integer I mean that so that no fraction results, so it could not be reduced any further. So that is how we mean by reducing to a least integer form. So 1 to 1 is the least integer form, and it doesn't have any fraction. So this is our final answer. The Miller indices of our directions are 1, 2, 1. You'll write the number that you got from x coordinate, then you'll write the number that you got from y coordinate, and then at the end from z coordinate. Okay, and they are written without any spaces in between them and enclosed in these square brackets, no commas, no dots, nothing else. Okay, so this is how you define the 3-index system and or Miller indices for directions in cubic unit cell. In next video we'll be doing it for direction C. I'll attach that video in the description box or in comment section. You can simply check out the playlist solid state physics English, solid state physics 1, 2, or whatever solid state physics playlist you'll open it, you'll find these videos in it. Okay, so yeah, goodbye, take care, like, share and subscribe.